So, charge distributions. So, in this situation, where we're looking at a sphere, so it's a 2D view of a sphere. All right, so we're taking a slice, if you will. It's hard to make a sphere, a 3D thing in this tool. It's called LaTeX. It's spelled latex. It's a typesetting language. And it makes book sort of stuff, and it makes cool slide stuff as well. But this is a picture swiped from somewhere. So let's pay attention to this slice here that's in red, all right, over here, based on a stretch from the center of the sphere. So, constant radius, obviously, as we go around town, and then there's going to be this change in theta as we consider a slice. So yes, we're aiming at some calculus here of this. And it's going to be important to realize that the height and the width of these chunks are obtained that way. Those are just x and y versions. Okay, you should know by now how to go from polar to rectangular given your math life. Well, that corresponds to, so remember, there's some spot out here that we're measuring, trying to get a feel for, the electric field at this point. And so it's some distance away from our central point, which means that the actual distance between the edge of things, okay, so just to get our bearings in the problem before we try to figure out or get to the math of it, all right? And then just to be clear here, the distance d equals r minus big R cosine theta is the distance of the center from one ring to the observation location. So rings of the sphere, meaning looking at it axially down this side of the sphere. So they'll have all these sort of concentric rings of different radius, right? So this should ring a what, a Calc 3 bell? Was that where you did rotations and solids and all that? Is that Calc 3 or 3? Whatever Calc it was. That one, all right? Now, the nice thing here is that, take a look. I can take that strip, that red strip that's in the sphere, and I can lay it out in Squareville here, all right, Rectangularville, and it has those dimensions. Okay, so this, pretty easy to see. As I squash it down, that arc length becomes r d theta. We did that last semester when we started with circular motion, torque, and all that jazz. And then full revolution, 2 pi r sine theta. So the area of that slice would have those dimensions. We could compute that with those parameters. All right, so that's the basic stuff. So amount of charge per ring slice, if you will. So remember, this is the charge density idea. This is a fraction, the surface area of the ring, as a part of the whole surface area of the sphere. That fraction of the total charge is what our chunk of charge is. So This is the second or third time we talked about charge density. We have to pitch it in terms of charge density in order to get into the calculus, because the calculus has to be about a dimension that's Cartesian. All right? So plug in Chugsville over here, and we get this, all of this constant stuff, just a bunch of numbers. So we know what our chunk of charge is in terms of radius, and the radius is going to change depending on which slice of the sphere we're dealing with. But calculus is our friend and helps us track that all pretty, especially if we have a computer that does it for us. So remember E, or a chunk of the electric field, okay, is going to be, well, here's K. So remember, that's what K is. And then it's a Q per R squared, and when you do all the math, and I'm not going to bug you with it, you get this whole business here. So this is where all the magic happens. All right? So now we can take that chunk of charge that's dependent on things like that, whatever angle we're at. We can also, D was defined, it's a slide or two back, as that. So again, we want to get rid of, because it's going to be hard to integrate with two variables, right? Isn't it more better to integrate with one variable than two? So this depends on which one you're doing. And so now we can, it's all in R and theta. Okay, R is a constant. So this, man, look at this. Good golly, Miss Molly, look at all this stuff. All right, yay team. Thankfully, you don't have to do this on the homework. The homework's remarkably simple in comparison. All right, so jamming all of that into the limit process and all that, so we will integrate with respect to theta. So here's our single variable in the equation. We do this integral, which I'm not going to do that. This isn't a calculus class, so you can look it up, all right? Or tell the computer to do it, even better. So we end up getting, well, good gosh. You know what that is? So this is the same as E for a point charge. If that's true. All right, so get this. A sphere of charge acts like a single charge at the right distance. That should make some sense. And we might suspect that, but until we prove it, it's not established. So the trick here is like the last time we crossed this bridge with the dipole, had that a similar thing. Also, the length of a rod is, when the length of the line of charge is larger or smaller than something, and how far away you are from the center of the dipole versus its displacement within the dipole. All those things matter for the field. And when you are within the constraints, then it works out. When you're outside of constraints, it don't work so good. You have to switch to something else. All right? So, and then inside, it's 0. And the math would bear that out as well. We'll have several ways that will come out why the charge or the electric field on the inside of something is 0. But the fact that all the charges want to get away from each other means they have to get away from, they wouldn't collect in the middle. Duh. All right? So that's